We've looked at finding the basic features of our ellipse and our hyperbola, tangents, normals, etc., etc. So now let's actually use it to do stuff. So the geometric properties. So the first property is this one. The chord of contact from a point on the directrix is a focal chord. Well, let's go and prove that one. So I'll do it for the ellipse. I mean, the hyperbola is very similar, but I'll do it for the ellipse. Now, they've told us T is on the directrix. Therefore, I know its x-coordinate is A on E. We know the chord of contact will mimic the ellipse. So it would be x naught, but instead of x naught now we've got A on E. Y naught on B squared. So we get x on AE plus y naught on B squared is 1. Now that's the equation of the chord of contact. We just have to prove now that it goes through the focus. It's a focal chord. So if we substitute in the coordinates of the focus, so A on E plus 0 is 1. So yes, the focus does lie on that line. So yep, it is a focal chord. So there's one property. That part of the tangent between the point of contact and the directrix subtends a right angle at the corresponding focus. Let's put that together with a picture so we can see exactly what they're talking about. So we're saying that part of the tangent between the point of contact, which is P, and the directrix, which is T. So remember, to subtend an angle, you get 2 points, draw it to a third point. So it's saying subtends at the focus. So we'll draw it up to the focus. So basically what they're saying is angle PST should be 90 degrees. That's what we want to go and show. All right. Well, we know the equation of the tangent. I've got it in the parametric form. So x cos theta on A plus y sin theta on B is equal to 1. Now, we want to find the actual coordinates of T. We know its x-coordinate is A on E. So if I substitute that in, I should be able to work out the y value. A little bit of manipulation. We get to this point here. You see the E minus cos theta over E. Which is like, oh, is there anything I can do with that? Not really. So best I'm going to do is factorise, I think. I can't see a way of simplifying that down using properties of conics or anything. So it's ugly, but that's what it is. B outside of E minus cos theta on E sin theta. All right, so I have coordinates for T. We know the coordinates of S. That's AE0. We have the coordinates of P. So I guess we just got to show that the slopes multiply together to give -1, and that'll prove it's a right angle. So slope of PS, B sin theta, A cos theta minus E. Slope of TS, that's a bit uglier. Well, I'll invert and multiply. So that the denominator I've turned into one fraction. So I've got A 1 minus E squared. Oh, that's so similar to something else, isn't it? If it was A squared 1 minus E squared, I could change that to B squared. But that's all right, I can still do that because I'll make it A squared but then divide it by A as well. So I can tidy that up. Now why on earth? Because remember, we're trying to cancel here and get rid of the B's and the A's and so on. So now I've rewritten it as A E minus cos theta over B sin theta. Right? Now you might not see it straight away, but the A squared 1 minus E squared, I've said, oh, that's going to be B squared, which will cancel with the B on top, leaving me with B on bottom. But then I've got A on the bottom of the fraction, but it's on the bottom of the fraction, so invert and multiply, I end up with the A on the top of the fraction. Now I have a look at the two slopes, and we can see that it is going to cancel. One's got cos theta minus E, the other's got E minus cos theta. So they will all cancel, leaving me with -1. Thus, yes, it is a right angle. So we've got algebraic manipulation. Potentially we could be using trig identities in these as well. But also the property of the ellipse itself might come in handy to solve some of these problems. The reflection property. You may remember the reflection property with the parabola. well, all conics have a reflection property. So the tangent to an ellipse at a point P is equally inclined to the focal chords through P. Well, again, let's draw a picture to make sense out of what that's saying. So the reflection property here is, well, remember the reflection property technically is the normals. But obviously if we prove those tangents are equally inclined, then the normals must be as well. So we want to prove SPT is the same angle as S dash P T dash. So let's prove it. I'm going to draw in another parallel line there, you see, going through P to help me out. And I'm drawing in now a horizontal. So I'm saying the ratio of PT on PT dash would be the same as PN on PN dash, and that's just using the ratio of intercepts of parallel lines idea. You've got three parallel lines there. It doesn't matter where we draw the transversal, it should cut in the same ratio. So our ratio of intercepts parallel lines. Well, if I rearrange that, I now have PT over PN is equal to PT dash over PN dash. Okay. Again, as I say, I'm going to use the idea of the definition of the conic, that PS dash is the eccentricity times PN and so on. So that PN and PN dash I've changed to PS on E and PS dash on E. Well, I can get rid of the E's, they're going to cancel. Oh, it's a strange thing to do. But have a look at the lines I'm now left with. PT on PS and PT dash on PS dash. Because remember, we just proved in the last one that that angle at the focus is 90 degrees. So they're right angled triangles, and this is the ratio of two sides in those right angled triangles. Right? So the secant of angle SPT must be the same as the secant of angle S dash PT dash. Now we know these angles are acute. So therefore they must be the same angle. If they've got the same secant ratio, got to be the same angle. So SPT does equal S dash P T dash. Alright, so that's the reflection property of an ellipse. I'll show you a video after this which is actually quite good about the ellipse. Here's a really interesting property. The sum of the focal chords is always 2A. I don't know whether you've ever done this before or not, but what you can do, if you were to get two nails and put a piece of string and keep it tight, you did that in physics? Yeah, and that's a way you can draw an ellipse. Well, this is why. Because those two distances added together will always be a constant amount. That constant amount has to be 2A if you think about it, because if P happened to be on the horizontal axis, then those two distances would give you the diameter of the ellipse. So it's always going to be 2A. Well, let's prove it. So whilst you might have done it in physics, I'm sure they didn't actually prove it in physics. There's a directrix. So PS I can replace with eccentricity times PN. And PS dash I can replace with eccentricity times PM dash. I can factorise out the A and I'm left with PM plus PM dash, which is that horizontal green line going between the two directrices. Well, we know the equation of the directrix is A on E, so therefore the distance between the two directrices must be 2A on E. So E times 2A on E is 2A. Therefore we get a constant 2A. Which then brings us to this sort of question now. Let's go back to complex numbers, where we're finding the locus of we could now look at this, and when we do see it now, we hopefully will recognise it to be an ellipse. So if you have a modulus plus a modulus equals a constant number, that constant number not being 0 like we saw in the multiple choice there, we're going to get an ellipse. Okay? Because we're saying the sum of two distances is a constant amount. So when we're talking about our vectors there, we're saying z is some random point, it's joined up to 2 and it's joined up to minus 2. So it's like saying 2 and minus 2 are the focus, and there's your random point, and we just said, well, if that's constant, it'll scribe out an ellipse. So now we just have to deconstruct this thing and work out all the key features. So 2a then must be 8. So I know a is equal to 4. AE is equal to 2. We know that. So 4e is 2. We now know the eccentricity of our ellipse. B squared is equal to a squared 1 minus e squared. So I now know b squared is 12. Well, that's pretty much it now, because that's going to be centred at the origin. I suppose that's the other key thing, is to work out where the centre is. That one's at the origin, so it's just going to be x squared on 16 plus y squared on 12 is equal to 1. Okay, so we have some out of Patel, we have some out of Cambridge 3D, some out of Cambridge 3F, but I'm not going to do any more theory till Monday. So we've got the remainder of our 3 periods today. We've got the double tomorrow for those that aren't at quad schools, of course. So it'll give us a chance to have a good look at some of these questions.